Hi everyone. So today I'm going to talk about linear functionals and the dual space. And so in this I'm going to be focusing on the intuition of the thing more than anything else. And so let's build this thing from scratch. Supposing I give you a vector, right? Not just one vector, a bunch of them. Like here, like here, like here. All right, so you have lots of vectors. Okay, so what these vectors represent is some kind of information. So what we want to do with these vectors is extract some kind of specific information from them. This is where linear functionals comes in. So what is that? What is a linear functional? It's just a function that takes a vector and then returns a number. So the input is a vector and the output is a scalar. What does this mean? Well, what it means is that it depends a lot on what this function is, right? So, what kind of function? A linear one. This is right in the title itself. A linear function is what we want. So what does this mean, linear? It means that it has to satisfy these two axioms. Is that the word? I'm not sure. It has to satisfy additivity, which means if you have a function f of x, v plus w, this is equal to f of v plus f of w. And it has to satisfy homogeneity, which means that if f of cv is equal to cf of v. All right, so this is these are the conditions, I guess that's a good word. These are the conditions that our function has to respect in order to be able to do this. So now let's imagine we're in 2D space. Okay, we have a vector, something over here, where you have x comma y. X and y. Okay, now let's take this vector and define a function f of v equals 3x plus 2y. This is a linear functional. What is this functional doing? It's taking your vector and probing it. It's extracting a number using weights. I think this is the key point here. You can change this, so 3x plus 2y, my bad. You can change this. It's extracting a number using weights. You can change these weights. This could be 5, this could be 6, this could be whatever number you like. So it's basically asking how much of this vector lies in a certain direction. Is that clear? I think that's the main intuition here. We have a vector, we pass it through this function spits out a scalar. It spits out the scalar by weighting each component of the vector with some number, some scalar number. Okay, so another way to think about it is a linear functional is like a measuring device. Different functionals, they measure different aspects. So you might see that one measures how far right you are. So this is functional alpha. Let's call it that, just for fun. Another might measure how far up, and so on. So instead of thinking about vectors themselves, we can all think about all the ways to measure them. And so this brings us to the idea of the dual space. What is a dual space? If you take all the possible linear functionals on a vector space, what is this? Just pause for a moment and think, what am I leading up to? So if you take all the possible linear functionals on a space, we're creating a new space. This is called the dual space. All right, so in our original space we have vectors. In our dual space we have functions that act on vectors. So the way this is written is V is the vector space and V star is the dual space. All right, so right, let's move on. Okay, so there's something really interesting about this. In finite dimensions, vectors and linear functionals are very deeply related. In fact, every linear functional can be written as a dot product with some vector. All right. So closing thoughts, this is basically what a vector space is and what a dual space is. And we'll go into this a little bit more detail next time once this has some time to sink in. And we'll solve some problems together. I think that's the best way to go about this. And yeah, that's all. So what we're going to do next time is connect this to matrices, dot products, and maybe quantum mechanics. I'm not sure if I want to actually go down the physics route, but that is kind of a more solid application and might help with the abstraction a little bit. All right, so yeah, this is the end. Thank you for listening.